Have you ever wondered how these amazing and spectacular self-driving cars drive around cities which they have never seen before? At the heart of these self-driving cars lies a fundamental concept called SLAM or structure for motion. The SLAM or simultaneous localization and mapping is an amazing method which lets these self-driving cars essentially build a three-dimensional map of the world around it. And the more spectacular thing, these can be done just with cameras, even just a single camera for that case. And in today's episode, we are going to deep dive into thinking how we can use these cameras to actually stitch a three-dimensional version of the world at the computing level. So let's dive right in to the world of PerspectiveNPoint and demystify it with me. So to just give you a simple example, on the top you see the video from a self-driving car. In this particular case, it's on a freeway, and on the bottom you see these dots which are basically being reconstructed as the car is driving along, which is representing those green points. And the red points are basically what is currently being seen, and the blue and the green lines are basically the camera moving in space and time. So as you see, in real time, this self-driving car can reconstruct the world, place itself in that map, and know exactly how to change the lane and what not to hit when there is a car nearby. This is spectacular, isn't it? Let's see how this is actually done. In the previous videos, we have talked about we have a bunch of input images and we want to reconstruct this. So what we did is we start with a simple scenario. We pick just two images. In this particular case, let's say the first two images when the car starts. And we take these two images, we estimate something called the fundamental matrix using the 8-point algorithm and then RANSAC. I would urge you to watch this previous video on linear triangulation to understand this concept really well. Then we estimate something called the essential matrix, and then we apply what is called the linear triangulation. So once we have this linear triangulation done, we basically disambiguate the camera pose because it gives us 4 solutions and we want to find the right solution. We take that and then we try to reduce the error by doing the alignment better using a non-linear triangulation. The catch is, this is only with 2 images. How do we actually bring in a third image into this stack, right? So what we do is now bring in a third image and we basically continue with this image, and then what we will study today in this video is linear PnP, and we are going to essentially bring this third view into the world view of the first 2 images. And then we will perform a non-linear PnP just to make it more accurate, and we will utilize these things to make a better 3D model in the future. So the question is, how do we add a third view? We have the same world model. We have this world point capital X, we have Iron Man looking at this point, and we have Captain Marvel looking at this point. They have reconstructed a 3D world view, and they have a good representation. But now Captain America comes along and says I also want to help. So how do we enable Captain America's view also to be added to this map Iron Man and Captain Marvel have built together? Let's look at that. So we are going to basically get the point capital X on basically Captain America's image frame by a shift matching feature correspondence, right? Okay. So what we essentially have is a 3D to 2D correspondence between small x and capital X. And we can apply the pinhole projection equation, which is simple, and this is a standard equation we have been seeing from the last few videos. And then we are going to call this K into RT matrix as the projection matrix P. So if we write out the pinhole projection equation, this is what it looks like. And clearly this equation is a linear projection equation in the camera matrix. Great, beautiful. And so we can multiply these things together for x, y, z, and x and y on the image plane points. And if we write it out, this is what it looks like. And the question is now, how can we use this to add it back to the Iron Man and Captain Marvel's frame of reference? Let's look at that. So first thing is, we want to find out the number of unknown variables. So in this particular case, we have 12 variables in the P matrix, but we also don't know scale. Remember that when Iron Man and Captain Marvel did this, they lost the scale lambda, and which was set to arbitrarily 1. So that's what we lose. So we have 11 parameters which we need to estimate. And every time we get a point here, we get 2 correspondences per point. So this means that we can basically, like, given enough number of points, do this for a third view, and it can also be done for an nth view. So we can like keep adding more and more superhero views, and we can reconstruct a 3D scene in a much better environment, as long as there is a correspondence between the current superheroes view and the current map. So let's continue with this equation. If we write this out as a linear equation, this is what it looks like. This is a 2x12 matrix, and what we can do is we can set this up in the form of a linear form, right? And this is for a single point, and if we do this for n number of points, this is what it looks like. This is fairly simple. It's a 2n/12 matrix for n number of points. So this is, like we said, it's a ax equal to 0 form. So this is fairly simple, but we know the camera calibration matrix K, so we can also estimate RNT. So the way we would do that is basically we write K into RT is equal to a scale factor which is unknown into the projection matrix P, and basically the rotation matrix is going to be obtained this particular way. And if we basically multiply the K inverse into the first 3 elements of the P vector, and we can do the decomposition of that, we can essentially recover the unknown scale, and we can recover the rotation matrix. Remember that the scale here we are obtaining is that of the Captain America's frame of reference with respect to Iron Man and Captain Marvel. It is not the metric scale. You do not get anything in meters here, right? When Iron Man and Captain Marvel did that, they arbitrarily set the scale to 1. Captain America's field of view is going to be with respect to that. Is it like 1, 1.25 or 0.8? That depends. Right? From that, we can also recover the translation and scale this particular way. The question now is, we did triangulation with 2 views. So we bring in a new superhero. We brought in Captain America. Why can't we just do triangulation between Captain America and Iron Man, or Captain America and Captain Marvel, and just call it a day? I want you to pause the video for a second and think about this. The answer is actually not so straightforward, but it's fairly intuitive once you know the answer. So let's bring in just Iron Man and Captain America here. And if we do the same thing with just Captain Marvel and Iron Man, you will see that the scale of the building estimation or whatever is completely different, right? Just to put it next to each other, the scale of Iron Man to Captain America and that of Captain America to Captain Marvel are completely different, right? They're self-consistent, but they're not consistent across these two things, right? If we take the scale and bring Captain Marvel back onto the left-hand side frame, what will happen is Captain Marvel will appear much closer than she actually was, right? And this is exactly why we cannot just keep doing triangulation. Because of the scale drift, your map is going to start expanding or contracting, and you are going to have weird artifacts when you try to do this. So instead, what we want to do is we want to recover the scale for the new view and add it back to the original view and scale it back in that particular way. And that is done through PerspectiveNPoint algorithm. So we need a minimum of 3 points to do the PerspectiveNPoint algorithm. Remember, this is where we had left off, where we had like the projection equation, we multiplied and we had 11 unknowns, and we had 2 correspondences per point. But since we know the camera calibration matrix K, we basically just need to find the remaining 6 degrees of freedom, which correspond to the RNT if you want to think about it that way, right? So the 3 correspondences are the minimum required to do this PnP when the camera calibration is known. When the camera calibration is not known, of course, you need a lot more. But in this particular case, we know it's a calibrated camera. We know the camera all these superheroes were using. Great. So let's take Captain America again. We basically are going to do the point correspondences between the point x1 and capital X1. And then we have another point. Remember, we need 3 points. So the distance between x1 and capital X1, that one is called d1. And the distance to capital X2 is called d2. And the distance between the world points x1 and x2 is called p12. Okay, and this angle subtended, which we know is basically θ12. We are talking about this triangle in blue, and we are basically going to apply cosine law in this case. Cosine law is fairly simple in this case. You have 2 sides and the angle subtended between them, and this is the relation you get. We can apply the cosine law again for a completely different point between x1 and x3. And we can also do it between x2 and x3. So we have three different world points, x1, x2, x3, and we apply cosine law 3 times. We have three unknowns, which is the three distances, d1, d2, d3, which we don't know, and we want to find this out. So this is fairly simple actually, because we know that these rays from Captain America's frame of reference to the image point is obtained through the ray equation from the projection by multiplying and normalizing, and you can obtain the same thing for the other ray. And if we feed these values into the cosine law equation, we know that the cosine of the angle between two vectors is obtained by the dot product divided by the normalization factor. So we know that this is fairly simple. So we can apply all these things together. So this essentially, when you feed this in, it will bring us to a fourth order polynomial where closed form solutions exist. And this can actually be solved in a very simple way. Just to quickly recap, we basically used the projection equations of three world points, and we applied the cosine law between the three world points and the image center. And when we combine all of these three things together, it's going to become a fourth order polynomial equations where solutions exist. So we can basically compute the translation using the three world points and the three distances using the simple formula here, and where we will basically know each of these x tilde values are given by the ray equations, right? And this gives us the rotation matrix. This gives us four solutions, just like what we had seen during the essential matrix decomposition. So what we need is a fourth point to disambiguate, and that is called the P4P algorithm. So P3P has a very special case where it fails when all the points are on a line, because the area of the triangle becomes 0 and hence it doesn't work and it becomes degenerate. And P4P similarly fails when all the 4 points are on a plane. Again, you lose 1 degree of freedom and it becomes degenerate. In practice, we don't do simple P3P or P4P because they're not really that robust and they're very sensitive to outliers. So what we can do instead is we basically do something called PnP, where n is the number which we can pick, and then we apply RANSAC along with that to actually remove outliers. The way we do that is we basically want to find the camera pose R and C so that they have the minimum reprojection error on the inlier set using RANSAC. In this particular case, we choose n is equal to 6 because this is one of the simpler versions of PnP, but there are obviously more fancier versions where you have different points and like different constraints which come in. So in the first case, we do the linear PnP where we minimize the algebraic error like we saw before. We set it in the form of Ax equal to 0 and we solve it for 6 points. And when we actually look at it, this is what it looks like. This is the view of the new points added on, and we'll see the image in a second. And this is basically for linear and non-linear. Once we do the linear thing, we get these red points. This is where the image was. So, but this is a good starting point, but it's not that great of a final answer. So what we want to do is, the linear PnP works well when the system is linear, but in practice it's not because we have divisions and projections. So what we want to do is we want to minimize the geometric error between the measurement and the projected 3D point. This concept of reprojection we utilized in the last video as well, where we saw the linear triangulation to become non-linear triangulation. I would highly urge you to go watch that video if this concept is not clear. So essentially what we are trying to solve is this minimization problem. We want to find the pose R and C of the camera in the new camera which we have just added. We know the points detected by SIFT in the current image, and we have the world points already from the first two views, which is capital X, and we are projecting it back into the world. And we are subtracting these two because they have to be the same, and that's what we are doing. In this particular case, the P3I refers to the row of that particular thing. Okay, so to solve this, you would use something like SciPy optimized least squares to make it easy. Again, in this particular case, this was using a rotation matrix, but in practice, we use a quaternion because it just works much better. Now let's do a comparison of linear versus non-linear PnP, and let's see how much of an improvement we actually get. So in the linear case, you see that like these red detection points from SIFT do not coincide with the reprojection based on the world point and to image point correspondences and projection from the first two views, and they're really off, which means that the scale is actually not that great at all. So in the nonlinear PnP, the scale gets refined much better. It almost looks like on the linear case, the green points are more zoomed out. In the right hand side, it's like almost pretty much perfect, right? And that's what we needed to do for perspective endpoint algorithm to bring basically a third view to the scale of the first two views. So this is basically where two friends have taken an image and they have reconstructed a scene, and a third person comes in with either the same camera or a different camera and takes a picture and basically wants to append to this 3D model to make it better. That's what we are trying to do here. So just to quickly recap, why do we need perspective endpoint algorithm? Essentially, why can't you just keep doing triangulation? What is the minimum number of points for perspective endpoint? Why do we need nonlinear PnP? See you next time. Take care. Bye-bye.